Building on a budget? Then you need to watch this video, because today we're talking about value engineering and how choosing the cheapest structural engineer is probably the worst thing you can do for your budget. I'm Dave Edwards with Earthbound Homes.
I'm Jason Powers with ZFA Structural Engineers.
And let's take it away. So thanks for joining us again, Jason. Appreciate you coming back. So we are actually often asked to provide a recommendation for a structural engineer on our projects. As we work with architects, as a builder, we are really focused on making a cost-effective building. And often that means really being optimal in the usage of materials for the structure of a building. Like a foundation, which we talked about earlier, you can spend a lot of money building a literal bomb shelter for a house, when in fact, that's really overbuilding for the need of that house. And I think it's important for us to understand this process called value engineering, which is designing exactly the right structure that you need for your house, and not making it overly strong and not making it under strong, and giving you a really safe, secure place that provides life and safety, but also doesn't break your bank or break your budget. And we brought Jason in to really discuss kind of what do you consider when you go into a project. I mean, how do you consider the budget of that project with relation to the structure of that project?
Yeah. Like we bring budget in right from the very beginning of our design process. That's obviously a very important design constraint that we want to keep in mind, and start working with the team to meet that goal for the budget of the project. Value engineering, you hear that word a lot. We talk about that, and a lot of times what that is the architect and engineer doing their thing, and then they do that for a while, spend a good amount
of time
and time, have a product, and then they give it to a general contractor who then prices it, and it comes in
always more expensive than the original budget.
Yeah. Yep. And then we talk about value engineering. Really, the ideal way to do that is to bring the general contractor in early in that process, so it is a real-time, ongoing conversation between that team, including the general contractor.
Right.
So I feel like value engineering is just an integral part of the project from beginning through the end, and you really need that team together from the early stages to keep that in track.
I think is super important, like Jason talked about, that, when we first started, we had a limited experience in value engineering, and what we were looking at were plans that if everybody's ever looked at a set of plans, they're very, very confusing. And the structural plan is even more confusing. And the more floors you add to it, the more confusing it gets, because admittedly, you have a lot more loads and a lot more things that you kind of have to include in your structural plan. And what we saw was, as we got more and more experienced in construction, we saw things that kind of seemed to be out of the normal. So, we would see the kind of same details over and over again. We kind of learned to understand those and why they were there. But then every once in a while, we get a project from an architect and an engineer where it just seemed to be so much more difficult and more consuming of materials and time to put that together, that we started second guessing the structural engineers. And it's not that we're telling the structural engineers what to do, because we don't obviously have that training, and it's not our butts on the line if the structural engineering is wrong, but it's understanding how they differed from the other projects that we saw. And one of the reasons that Jason and I work so well together is because we have this conversation all the time. Hey, like, we thought about this. Can we do this? It will help us get rid of the steel on this project, because steel in construction is very expensive. It's much more expensive than wood, but it's also highly conductive, which is a real problem in the exterior envelope of a house. And so we were always kind of looking to have those conversations with you. And we as a builder like to use engineered lumber as opposed to normal stick lumber. So a normal 2x4, 2x8. The bigger the material, the better it is to use engineered lumber, because we can use smaller trees that are faster growing and they're more stable. A lot of people don't probably understand that a 2x8 floor joist doesn't stay straight and true. That after it starts drying, it starts warping and twisting. And that becomes a real problem because it can lead to squeaks in floors and deflection and drywall cracks and nail pops in drywall and all kinds of problems. And so it's having these conversations with the structural engineer that really expands everybody's skill set, because we're talking about details that most people don't really understand. And honestly, a lot of architects don't delve into the details like the structural engineer does, right? Like, you're looking at every clip and every beam, and we're having to price all of that. And so the better we can get at reducing the things that are not necessary, the more cost effective that project is for the homeowner to pay for. Does that make sense?
Yeah, for sure.
So
perfect sense.
Tell me about, I know that when I first started, we were designing projects based on, and this was 20 something years ago. I don't feel that old, but I am that old. We were designing things on the kind of prescriptive code, but in a conversation with you, prescriptive code isn't really relevant anymore.
It's not. Prescriptive code really isn't allowed in seismic country, which is the majority of California. Because of the seismic forces that we designed for, and the permits that are required to do these homes. You need a structural engineer for that.
So the code that you could build a house in Iowa that tells you the size of the headers over the windows and doors and the floors and all of that just doesn't work here, because we have so many different forces on these buildings. We really do need a structural engineer, even if we're doing small modifications.
Yeah, indeed. That's just for the superstructure too, and then that's, like we've talked about in other conversations, the soil is also very varied and diverse, and another thing that needs specific structural engineering to design a well-built house.
Right. So then how do you deal with, or how do you approach value engineering on your projects? I mean, you don't ever, I think, go out and get pricing from a framer or a structural steel guys. So you're really having to depend on the feedback from the builders that you work with, right?
Yeah, that's crucial.
So then, what is your process for designing a structure and really trying to value engineer it in the most effective way possible?
Well, right from the beginning, as we discussed, we would like to have that team working together. That is vital. That the general contractor is involved in that process to create a conversation loop where we're iterating on the design, but getting that feedback on what's on the cost. Also, keeping the design in check too. That's making sure we're keeping in line with the budget for the project.
So keeping the design in check, the structural design or the architectural design?
Both, really.
Oh, really?
They need to go hand in hand. The structural follows the lead of the architect most of the time, but sometimes if for budgetary reasons, there might be feedback loop there where we coordinate with the architect to say, if we could get a little bit more wall here or this, we could remove a steel frame and change that to a more conventional and less expensive wood shear wall.
So, like, for instance, you have a wall that has a big door in it. You only have 18 inches of wall on each side of that big door.
Yes.
And if you just made that 18 inches bigger, you could use wood instead of steel.
Yeah. If we had, say, 6 inches on each side, 24 inches, that could be a more simple wood framed seismic element, as opposed to a larger, more expensive, more complicated steel beam.
So literally those 6 inches can be the difference between tens of thousands of dollars.
Yeah, so it's a simple conversation, but it's not one that is often asked. At least it's a conversation with the architect and the homeowner to say, hey, is this worth it for you? If you want the slightly wider opening, we can do it. But if you want a slightly less wide opening, with hopefully not compromising the architectural vision too much, we could also make a more cost-effective structure and building.
So one of the things that we do a lot of is, and as I talked to earlier, is that we're using engineered material. So we're using I-joists, we're using open web floor trusses and roof trusses. And a lot of times we see, especially in spec building, which is very interesting, you see a lot of like 2x6 floor joists with girders all the time and all of that. And we've never used that typically because we're trying to reduce the amount of foundation work that we have to do. And we find that framing with engineered lumber is actually a lot more accurate and a lot stronger, but there's also a component of those engineered beams and trusses that have to do with our ability to work projects with the electrical and the plumbing and the HVAC, the heating and cooling systems through the openings in those materials, right? Because isn't it correct that like a 2x8 floor joist, you really can't drill very many holes through that to get all of your wires and plumbing ducts running through there?
Yeah, for sure. There's not much room left in a 2x8 to be cutting too big of a holes through there. You have to keep them pretty small. Definitely no ductwork going through 2x8. So these modern engineered products that you're speaking of really are designed for that, designed to allow for these bigger penetrations. And they're more stable, more accurate, which tends to make everything easier, right down to the finishing aspects of the project. If your ceiling is straight or your walls are straight, it's a lot easier to get the finished product that you're looking for, as opposed to some of this raw sawn lumber, which isn't as capable from a structural standpoint. Also takes a lot more finagling to get the finishes looking good sometimes too, right?
So it's actually, so actual sawn whole trees are not as strong, just in their bare manner, they're not as strong as the engineered products.
No, they're not, no.
So we get a better product that's also stronger for the same structural member.
Yeah, it makes a lot of sense. Typically, that engineered lumber is a little more expensive up front, but I think when you look at the bigger picture, it probably pays itself back.
Yeah.
Yeah.
What do you like better? TJIs, which are the eye joists that kind of look like an eye with a top and a bottom cord that are really the structural members, and then you have the OSB that kind of sets down the middle, and we'll overlay a picture like this, versus an open web floor truss, which is essentially two parallel, typically 2x4s or something like that, with webbing that goes across, and we'll also overlay a picture of that. Mm-hmm. What do you prefer structurally for those?
We try to find the product that meets that it best fits that particular project. So, either one work really well. I believe the eye joists are typically a little less expensive, a little more commonly seen, but there are certainly circumstances where longer spans, where we know there's going to be a lot of mechanical work needing systems going through that particular floor, where those open web joists are really handy in those situations.
I found it's interesting. We've typically used the eye joists in the past, but what we're finding is that the open web floor trusses on a lot of our modern style houses give us a lot more flexibility on where to run all of our electrical and plumbing and HVAC. Because often the modern style houses don't have attics. And so that whole kind of way that we normally run pipes and wires through a house is close to us. Literally, there's no space there.
Yeah.
And a lot of projects are on slabs. We typically like crawl spaces, but we don't want to run our ducting for our heating and cooling systems through the crawl space, because that's where basically rodents and bugs and potentially radon comes up. And so we're moving more towards the open web floor truss, just on a basis of trying to make our projects easier to build long term and make them more effective, because now we can keep all the mechanicals, which is the heating and cooling systems, within the insulated envelope of the house. So any air leakage from those doesn't go outside, it stays inside and works to still condition the house. That's
how we're learning to build better with your expertise in building envelope and bringing that together and adding that to the necessary structural design. We're finding better ways to build.
Awesome.
Yeah.
So tell me about how you deal with projects that have a lot of structural steel. So I know that typically a project that has long spans, big clear open spaces, maybe big cantilevers, requires a lot of steel. But we also know that steel is highly conductive. Are there opportunities to replace that steel with wood, and how do you account for that?
Yeah, that's a good question. So oftentimes what drives steel design in these custom homes is the architecture. It's very often very contemporary, modern designs that are looking for wide, long spans, large fenestration openings, as you mentioned, big cantilevers, and sometimes and then combine that with thin profiles. They often like to see,
yes,
thin roof eaves. and floor lines. So really the only way to meet those long spans in thin depths is with steel. So we get pushed that way oftentimes to make the architectural work the way that they would like it.
Got it.
And there's a balance there, which is another reason to have that full team together early on to talk through how we can create a beautiful building that the architect wants to build, but also one that's like energy efficient and
cost effective.
Cost effective.
So it literally, again, inches here or there, 2 inches on the floor may cause us to have to go with steel. Whereas if we had a 16-inch thick floor diaphragm, we could go with wood and it'd be more cost effective and also more efficient.
Yes.
Interesting. So really, your job is really comes down to inches everywhere.
It does these days. Yes.
So why is it we've kind of lobbed this idea around that steel and wood are different materials that can overlap in function, but why is steel a stronger material than wood? Like what characteristic about it makes it more strong for these types of projects?
Well, steel, without getting too technical, I mean, steel has the ability to, in a short, compact section, do so much more work. Is that because of the nature? 15 times more stiff than wood in general.
Okay, so the material itself is actually much stronger, stiffer.
Yes.
But is it also that we can shape steel in ways that we can't shape wood?
That's true. It's definitely shaped in the most optimal form for a structure to use. Similar to that's where the LZI joists that you were mentioning come into play. They're modeled after steel wide flange sections, where you've got the cords on the top and bottom and the web in between. It's a very efficient structural section there.
And from my understanding, the web is really there just to keep the cords apart from each other and to tie them together.
Provide shear resistance in the end, but at the ends and the points. But
so that's why we have the diagonal bracing on the open web floor trusses, is because that also provides shear.
Indeed, yeah.
Okay, so now that makes a lot of sense. So in modern construction, we're also seeing a lot of projects, especially in California, and I've seen other projects in other states where it's not the case, but we're seeing a lot of metal clips and straps that connect everything. So, you walk into a new house and it's no longer just studs and top plates and floor joists, it's studs and top plates and floor joists and a whole lot of steel everywhere.
Yeah, little metal clips everywhere.
Right.
Yes.
So what do those metal clips do? In short, I know there's about 250 different little metal clips and straps and everything. So what in general do they do?
Now they make it relatively simple and cost effective to attach one type of wood member to another, say a roof rafter to a wall stud. So they do make it convenient and relatively cheap. I think where the problem lies is that it's easy to just have those be everywhere, whereas as we know that's maybe a less thoughtful structural engineering approach. And in all ways, if we can find the places where they're needed to meet those goals of life safety, and also equally important, find the places where they're not needed and not use them there, rather than just doing a blanket design. That might cost a little bit more up front in the design side, but it makes it so much easier and cost effective to build the house.
Right. Yeah, it's been interesting to watch the evolution of construction over the last 20 years in California and see how, there's a clip that we use called an A35, and it used to be every 24 inches on the top of the walls connecting the eaves or the roof to the house, and now it's like on studs and openings and headers and floors and everything else. And it's just been an interesting evolution, as we talked earlier about the kind of evolution of code and understanding how these different forces come in on a project to really kind of take apart an old design, and we're adapting the new code to address those additional forces so that our houses become more safe, more effective, more cost effective. Because if your house falls off a foundation in an earthquake or gets majorly damaged in an earthquake, there's really no way you can put it back on the foundation.
That's the least sustainable thing you could do.
Yeah, so a little bit of investment now is a huge yield later on.
Yeah, resilient, we like to talk about for sustainability from a structural perspective is in large part designing a resilient structure that can last a long time.
I think that's really key. So if you're interested in learning more about structural engineering or building science, or you're interested in following these projects that we have on our site, or having these conversations with Jason or other professionals. Please subscribe, and we'll show you how to build a better way.